Okay, so chapter 20, we start the first law of thermodynamics and different thermodynamic processes. So we're going to apply the first law of thermodynamics that says the heat into the gas plus the work done on the gas is changing internal energy of the gas. So to visualize that, we think of a piston, and you can push down on the piston, and then there's some gas here. So when you're pressing down on the piston, you're doing work on the gas. Right? You're pressing down. So you're doing work on the gas. And if you're also pouring heat into the gas, so maybe there's a flame here. So you're pouring heat into the gas. The combination of doing both is going to tend to increase the internal energy, which means the agitation of the gas is going to increase and its temperature is going to increase. You see, so both of them, pouring heat into the gas and doing work, will cause its energy to increase. And when the energy increases, the temperature increases, because temperature is a measure of the average kinetic energy of molecules, right? So the other way this can be written is to say work on gas. Let's say you can say Q into gas is negative Q out of gas. So we can write it as negative Q out of gas. So then you can take this and take it to the other side. And then you can say work on gas is changing internal energy of gas plus Q out of gas. So is there any difference? Like, is there situations where this applies well and this doesn't, or this applies and this doesn't? No, they're both apply every time. But this might be more appropriate for some situations versus this. In other words, for this kind of a situation where you're pressing on the gas and you're putting heat in, this is the best form of the first law, right? Where a situation where you're only pressing down on the gas and you're not putting heat in, so you're pressing on the piston, then what's going to tend to happen? If you're not putting heat in, the internal energy of the gas is going to increase, but some heat will be expelled out, right? So the heat will escape. So in that kind of a scenario, this is the more appropriate form of the first law. Because rather than saying you put negative heat into the gas, it's better just to say that the heat was expelled from the system, from the gas. So this is positive now. Expelled heat. From gas. What if this is the scenario that happened? You put a flame and you put heat into the gas, but you didn't press on the cylinder. And the gas now did agitated and did positive work on the cylinder. And so now the gas is the one doing work on the cylinder. Right? So then now you are putting heat, but the gas is doing the work. So then we can write this as what? Q into gas minus W by gas. See, so work on gas is negative the work by the gas. You see? So then that's equal to change in internal energy of gas. So then this guy goes over there. Q into gas is delta E of gas plus work by gas. So that means if you put in, let's say, 100 joules of energy, of heat energy, right? And if the gas did 60 joules of work, that means the internal energy of the gas will increase by 40 joules. Okay? Whereas here, maybe you put in 100 joules of energy, and you did 60 joules of work on the gas. See what's happening? The difference here, you're putting in 100 joules of heat, and you're not doing work on the gas. So that heat that you're putting in is going into the gas doing work, and some of it is going into the increase of energy of the gas. Here, you're putting in 100 joules of heat energy, plus you're doing 60 joules of work on the gas. So then what's going to be the change in internal energy? So 100 plus 60, 160. So in which scenario will the gas heat up more? Exactly. You're putting in heat plus you're pressing it. It's going to heat up more. Here, you're just putting in heat, but because the gas is expanding, it's not going to heat up as much because it's occupying more space. So as the gas is expanding, it could be that less of it goes into the internal energy of the gas, and you're allowing the gas to do work. Now in this scenario, let's say you're doing 60 joules of work on the gas, and how much is escaping? That case maybe 40 joules escaping, something like that. Then 20 joules, so this one doesn't heat up at all almost, because the work that you're doing is good and a lot of it is escaping. So it depends on how much of it is escaping, of course, and changing internal energy. Now, there's some cases, let's see if there's any other case can we think of. You're putting in 100, it's doing work. Can we think of a fourth one? In other words, this one I was pressing and I was putting heat in. This one I was pressing, not putting any heat, and the heat was escaping. Here I was putting heat in, and the gas was doing work. It seems like there should be a fourth one. What would that be? Like another scenario where gas is the one doing the work. Maybe something like this. Gas is doing work. I was going to say the gas is doing work plus the heat is being expelled. Could that happen? You might think, well, why would it even expand if maybe it's a hot gas? Maybe I've originally heated up the gas a lot, and now it's so hot that that gas is able to do work on the piston, and it also expels heat out. Yeah, so the direction of the arrows is this way. So what's going to happen to that gas? It's going to cool down a lot, you see? So then what happens, what form of the first law is the best one for that? The work is done by the gas, heat into the gas, Q into the gas is actually negative, right? So then this becomes negative Q by gas is delta E of gas plus work by gas. So then we can say the best way to write it, take this over there and then bring this over here. So maybe negative delta E of gas is Q by gas plus work by gas, and then delta E of gas, negative Q by gas, oh, I should say Q Q out of gas, I should say, Q out of gas, out of gas, plus work by gas. You see? So delta E of gas, negative Q out of gas plus work by gas. So what's going to happen, it's going to cool down a lot in this case. If let's see here, if 100 joules of heat are expelled out of the gas and the gas does 60 joules of work, the change in internal energy of the gas is negative 160. So does this actually happen? Yeah, in the car Otto cycle. So in chapter 22, we're going to cover the Stirling engine, the Otto cycle, and the Carnot cycle. The Carnot engine, the Otto engine, and the Otto engine is one example of a car engine. Okay, so what happens in a car engine? You press the gas and you ignite it. That's the first cycle, the ignition stage. And it becomes really hot, very condensed. And all of a sudden then you allow the gas to expand. Then the gas expands and expels out heat. That's part of, that could happen. So definitely, then it cools down a lot, you see, by doing that. So, yeah, so those are like the four major and general ones. Then there's specific different types of processes that we can take, known as isobaric, isothermal, and isovolumic. Isobaric means allow the gas to expand or contract at constant pressure. So allow the gas to expand or contract at constant pressure. So all four of these can be done isobarically, all four of these scenarios, right? So this one I'm gonna just go like this. So what's unique about isobaric? Well, the PV diagram of isobaric looks like what? We write down pressure versus volume, okay? And this could be liters or atmospheres or pascals. So we're usually gonna use pascals here. Pascals. And this we're going to use meters cubed. So if you're letting it expand isobarically, it's going to go like this. Contracting isobarically, it's going to go the other way, right? So if it's going this way, that means you're letting it expand isobarically. So what's the work done by the gas in that scenario? If the gas is expanding, the volume is increasing, the gas is the one doing the work, right? If you're contracting it isobarically, you're the one doing work on the gas, you see? So the work done by the gas is the area under the graph, you see? Work is integral of pressure dV, right? So this is the physics 2 equivalent of the physics 1 equation. In physics 1, we say work is integral of force times displacement, right? So this is going to be Newton meter, which is a joule. So what we're doing in physics 2, since we're dealing with gases, we divide this by area and multiply this by area, right? And then force over area is pressure, and area times the dx is volume, an increment of volume, you see. So the units of this still becomes joule, PdV, you can see. So since the pressure is constant, then it's just going to be what? The pressure can be taken out of the integral, then you have integral dV, right? So then it's just going to be P V2 minus V1. So that's the work by the gas. So you see where it says work on gas or work on gas or work by gas or work by gas. So depending on which one is happening, if you're doing isobaric process, you can just say the work by the gas is P V2 minus V1. The pressure is not changing. Okay, how about isovolumic? Also called isochoric. So in that kind of a case, the PV diagram looks like what? V1. So that one, the volume of the gas is held constant, right? While you're pouring heat into it. So it's just going up V1 to V2. If you're pouring heat into it, the temperature is going to go up, right? But the pressure is going to go up and the temperature is going to go up, but the volume is going to stay the same. So all of these can be done isovolumically too, so that the work of the gas is going to be zero, right? So basically this one is zero, but so all the heat that you put into the gas will go into changing the internal energy of the gas. You see? This is the quickest way to heat up the gas, because you don't allow the gas to do work. So all the heat you put into it goes into internal energy. So if this is zero, or this is zero, or that's zero, or that's zero. So the work done is zero. So all the heat into the gas goes into increasing its temperature. All the heat into the gas goes into increasing its temperature, so it's the quickest way to heat up a gas. So or vice versa, if you're going down, it would be the quickest way to cool down the gas, right? So heat up a gas or cool it down. Okay? So then there's isothermal. Which is going to be what? Constant temperature. So what does the PV diagram of that look like? Have you guys done this in chemistry? No? Chem 101?
A little bit.
Huh?
Not so in depth.
Oh yeah? But you mentioned isothermal? Yeah? Okay, so isothermal, constant temperature. So what does the PV diagram look like? Well, remember ideal gas law, PV is nRT. So if it's constant temperature, this is a constant. I'm holding the T constant. So the PV diagram looks like what? Constant over V. So it's a 1 over X graph, right? V1, V2, this is P1, this is P2. So then you're going to have P1, V1 is equal to P2, V2. Okay? So now if you're going this way, that means the gas is the one doing the work. And if you go the other way, you're the one doing the work, right? So then what's the area under that graph? So now it's going to be an integral, right? Integral P dV, right? Work by gas, P dV. What's P? P is equal to nRT over V, where nRT is a constant, right? The temperature is not changing. So nRT over V dB, right? And since nRT is a constant, it comes out of the integral, so then you get an ln function, ln of V2 over V1. Now, the next one, there's also adiabatic, but adiabatic we're going to cover in chapter 21. So let's finish this. Adiabatic is going to be no heat into the gas. So adiabatic, we're going to have to introduce the difference between monatomic gas, diatomic gas. There's a little bit more theory to discuss when you're discussing the adiabatic process. Specific heat of a gas at constant pressure, specific heat of a gas at constant volume, the gamma factor, the difference between polyatomic, monatomic, and diatomic. But when you're doing isobaric, isovolumic, isothermal, those stuff don't matter, okay? So let's do an example and do a whole cycle. Let's take a chamber of gas through a whole cycle. Let's say you have here T1. So let's say you take the gas through these three processes. You heat the gas isobarically to 3 times the volume. Then you cool it to its original temperature isovolumically, and then bring it back to its original state isothermally. So as soon as you're seeing those wordings, of course your brain is going to confuse what's happening. So you have to draw a graph to interpret what's happening. Otherwise you'll get completely lost, you know. So we're starting at some P1, V1, right? So this is 2 atmospheres. Then we are isobarically reheating it to 3 times the volume. So this is V1. So 3 times the volume would be something like 1, 2, 3, 3 V1 isobarically, right? Then we are cooling it to its original temperature. So I don't know how far down I have to go, but for now I'll just go something, like that. Okay. And then I'm going back isothermally, right? So this has to be a 1/x graph, right? So I can ask now, what's the work done in each stage? What's the work done by the gas? What is work done by gas in each stage? B, what is the heat into gas in each stage? C, what is delta E of gas in each stage? And then D, what is the work total by gas, delta E total of gas, Q total into gas, and the efficiency of this engine. Nice problem. This is thermal. Love it. So I'll let you copy all that down. Okay, so before we start, we need to calculate some of the initial state variables of those are called state variables. P1, V1 is nRT1, right? So we need to know the initial state variables of the gas, what the gas is doing in the initial state. So we already know the initial pressure, we know the original temperature, so it would be good to know the original volume, right? But since I want to prefer the work in pascals, I'm going to convert. So I'm going to say T pressure 2 atmospheres. Remember what 1 atmosphere was? Now we go all the way back to chapter 14, 1.013 times 10 to the 5th, right? 1.013 times 10 to the 5th. Then the original volume, we don't know. Number of moles, 25. Gas constant, 8.314. Right? 0.314. Temperature, 25 plus 273, 298. Okay, so you've got to work with Kelvin. Okay, so put that all in. Point 3.